Hey everyone, so this is going to be the last video for this unit where we're going to talk about what's something called the 111 method. Now this is actually something that's a little bit unique to this class, so if you know people in the other class or you try to talk to people who haven't had me, they might not know this exact phrasing. But this is something that's going to be used mainly in this unit at least, mainly for the circular motion topic and the gravitational force topic, but it's something that is actually going to appear in pretty much every unit from now on. Mainly, what ends up happening is that every now and then you're going to be given a question where they don't give you numbers, or at least they won't be looking for something. Most of the time, you've been given questions where they say, if the mass is this and the acceleration is that, what's the force? Or something like that, where there's a clear end goal. What they'll do now is they'll say, hey, if we change this term, how is that going to affect this other variable? If we double the mass, how is that going to affect the force? If we triple the speed, how does that affect the distance? It's a very important thing that we have to worry about. One of the common mistakes that people are going to do is that they're going to set up proportions, and it doesn't work because that only works in very, very specific cases. So what I'm going to do is I'm going to teach you the 1-1 method. So a good example is something like this. They could ask something like, hey, how would the force change if the speed is doubled? Or I can go one step further and say, how would the force change if the speed is tripled and the distance is doubled? Something like that. So in there, they're not giving you any real numbers. Now, if you wanted to, you could actually just make up numbers and do the calculations that way. So if you're given this question and they're talking about circular motion, let's say, you can make up a mass, say that if the mass is 4, the speed is 2, and the distance is 3. Plug these in to figure out what the force is. I think in this case it would be something like 16 thirds. And then you would redo the calculations, doubling your velocity, and then seeing what you get for your new force, and then comparing these two answers. Now that's a lot of work for a very basic and straightforward multiple choice question. So the 1-1 method helps cutting down a significant amount of work. So these are the following steps. The first thing that you want to do is read the question to figure out what things are being changed and what equation you're going to end up using. And then you're going to want to write down the equation. I know that seems a little basic, but it's important to remember to write it down just so that you remember what terms are being squared and you can kind of work through all the variables. Now, this is where the 1-1 method comes in. You're going to read the question, and when you look at anything that wasn't changed in the question, you would plug a 1 in for that to say that it stayed the same. Mainly because uh, anything times a 1 is itself. 4 times 1 is still 4. So putting in a 1 means that that variable, that number, was unchanged. And then whatever did get changed, you would plug a number in to represent what the factor that is. So if they say that something was doubled, you would put in a 2 because it's 2 times the number. Tripled is 3, quartered is 1/4, and so on and so on. So a good example is, let's say they said that the speed was tripled and they want to know what happened to the force. Uh, in a circular motion type question, we know the equation is mv squared over r equals the force. There's nothing about the mass changing. We said that the speed was tripled, so that becomes a 3. I don't forget my square, that stays there. And my distance also didn't change, so that's still a 1. So then my answer is going to be 1 times 3 squared times 1, or divided by 1, is 9. Now, this doesn't mean that my force is 9. It means that my force is 9 times greater than it was before. So if my force was 2 newtons before, now it's 18 newtons, 9 times the original. And that's pretty much what this is. The important thing to remember, though, is that you're not using any real math. All you're doing is plugging in the factors that each of these numbers changes by. So if it doesn't actually change, it remained the same, you plug in a 1. If anything got doubled, you plug in a 2, and so on and so on. Sometimes they may give you numbers, but you pretty much go back to the same idea. So here's the first question. Pause the video, work itself, and we'll go over a second. All right. So again, reading the question, they explicitly say the word circular motion. So that means I'm going to be using the centripetal thing, centripetal acceleration or centripetal force. They're talking about speed and force. So I'm going to use the altered form of the equation, the one that goes mv squared over r. Uh, they only mention that the speed is doubled, but they don't say anything about the mass or the radius changing. So we're going to plug a 1 in for both the mass and the radius, and a 2 in for the speed since it's doubled. Doing all the calculations, we get that the force becomes 4, or it becomes quadrupled. So a lot of times you want to try and keep with the terminology. They said doubled, so we want to stick with words like quadrupled or tripled or quartered, things like that. But that's it. Here's the next question. Pause the video, work itself. We'll go for a second. All right, so here we have a theme park that's decreasing the radius by half. So when we use our equation, we're going to put a 0.5 in for the radius. Now for part A, they say that the velocity stays the same, and we want to know what factor the acceleration changes by. So we use the equation. We put a 1 in for velocity since it didn't change, but we put a 0.5 for the radius, and we get that the acceleration is doubled. Now, this ends up being a really big thing because if you are a designer of a roller coaster or a ride or anything like this, and you make a change like cutting down the size of a loop-de-loop, you need to know how that's going to affect acceleration. We mentioned before that when you are going around in a circle and you're experiencing acceleration, there's a limit to how much your body can withstand. Typically, it's around 9 G's or 9 times the acceleration of gravity. So if you built a roller coaster where the acceleration due to gravity is, let's say, 5 or 6 G's, which is still fairly high, then decreasing the loop-de-loop by half essentially brings that acceleration up to 10 to 12 G's. So there's a good chance that you might actually kill someone by making that change. So in part B, we say, okay, well, how would I have to change the speed so that the acceleration doesn't stay the same, doesn't change? So we do the same thing. This time, the 1 goes in for the acceleration, and now we're going to figure out what we'd have to do with the velocity. Obviously, we're going to have to decrease the velocity, but the exact amount is we'd have to decrease it by 0.71. So the velocity will now be 0.71 times slower. You could also rephrase this a different way, like 70% the original speed becomes 30% lower. It's about 3/4 of the original value, anything like that. Here's the next question. Pause the video, work itself, and we'll go over in a second. All right. You may have noticed that the numbers are changing a bit. Like I said, I'm kind of combining everything about the 1-1 method into one video. So there's a little bit from the centripetal force topic and a little bit from the gravitational force. So just if you're following along on the notes, just pay attention to that. So here, again, they mention gravitational force. So now we're making a switch over to the big G equation. They say that the distance is doubled, but they don't say about anything else changing. So again, we're putting ones in for any variable that stays the same. We are not going to put in the 6.67 because we don't put real numbers into the equation. We say G doesn't change, so that's a 1. M didn't change, so that's a 1. And M2 didn't change, so that's a 1. So we get 1 times 1 times 1 divided by 2 squared, or 1/4 or quartered. So doubling the distance quarters the force. which is pretty interesting compared to the centripetal force equation, where doubling the distance would have halved the force. All right, here's the next question. Pause the video, work itself, and go in a second. All right, so here they tell us that we're being transported to a new altitude above the Earth's surface. They want to first figure out what happens to our mass. Well, it doesn't change. If our mass on the surface of Earth is m, then everywhere in the universe our mass will still be m. Remember, mass never changes. Now, for the next part where we figure out our new weight, I'm going to go back and use the big G equation. Now, here's the thing. We know that the G, the M1, and the M2 should all be ones. But what do I plug in for R? A common thing that people will do is they'll see this word twice and think that R becomes 2. But let's draw a before and after picture. Before, we were standing on the surface of the Earth, like this. And we were 1 Earth radius away from the center. In the next part, we're over here. We're at an altitude of twice the Earth radius. So from the surface of the Earth, we're now 2 Earth radiuses away. But remember, this equation isn't to the surface, it's to the center. So my total distance is 2 plus the Earth's radius. So my distance actually gets tripled. It went from a distance of 1r from being at the surface of the Earth to a distance of 3r, which means that my weight ends up decreasing by a factor of 9. It becomes 1/9 of my original weight. So if my original weight was W, it's now W divided by 9. Try and keep an eye out for phrases like that. It's one of the few ways that they can kind of try to trick you. Here's the next question. Pause the video, work on stuff, and we'll go over in a second. All right, so same thing. They're looking at the gravitational force. They mention that only the Earth is twice as massive, but everything else stays the same. So it doesn't matter which mass I make it to. I just need to make sure that one of the masses becomes a 2. So I have 1 times 2 divided by 1 squared, and I get my gravitational force is 2. So it becomes twice as great. Here's the next one. Pause the video, work itself. We'll go in a second. All right. Again, reading the question, the only thing that they're mentioning is that the distance to the center becomes starts off as a distance d and then goes to a distance 3d, but it doesn't seem like anything else changes. So once again, I use the equation. I put a 3 in for the distance. I don't put in 3d, I just put in a 3 because again, that's all I care about. And I get 1/9. So if my original force is F, my new force is 1/9 of that original force. Here's the next one. Pause the video, work stuff. I'll go over in a second. All right. Here, they kind of changed it up. Now we're actually looking for what the value of R has to be so that the force is quadrupled. So using the equation, I'm going to plug a 4 in for force and solve for R. So moving everything around, doing some, math algebra stuff, I get that R has to be 1/2. So again, starting at my distance d, it is now 1/2 of this distance. And here's, I think, the last one. Pause video, work stuff. I'll go over in a second. All right. So here's a little bit difference where now they're giving us a number. So they're giving us a force of 20 newtons. Now again, this number does not go into the equation. If we're doing the 1-1 method, no real numbers. So the first thing I do is the same thing I did before. I write my equation for the force of gravity. It says that both masses are doubled. So I put a 1 in for everything else, but both M1 and M2 become 2. I do my math and I get that it's 4. Then I take that 4 and multiply it by the original force. As I said, the 4 just says that it's for times the original. So it's 4 times 20 newtons or 80 newtons. So this is what my new force is going to be. 80 newtons when both masses get doubled. Uh, that's pretty much it for the 1-1 method. There is one last thing to look out for. Like I said, sometimes they throw numbers in here. So instead of saying that the mass is doubled, they may say that the mass originally was 2 kilograms and now they're both 4 kilograms. And again, the idea is that you're looking for what factor the numbers change by. I have seen a few times where they'll throw in really crazy scientific notation numbers. And again, the idea was to realize that you either doubled the distance or have that number. But the main thing is to realize that if you ever see a question where something is changed and they want to see how that changes something else, that is a clear indicator that that's a 1-1 method. So keep an eye out for that. Now, there is one last thing that I want to talk about. I don't want to really spend a video on this, so I'm sneaking in at the end of here, which is all about elevator rides. So, one of the things that you need to be able to do, again, it's a one off question, there's no math involved here, it's all conceptual. You have to be able to recognize what happens to forces when you're in an elevator. So, really quickly, as a side thing, you need to know that scales don't measure your weight. I know that might be seem counterintuitive, but if you think about it, it makes sense. If someone puts their hands on your shoulders and pushes you down, your actual weight doesn't change, but the scale reading would change. What the scale is actually reading is your normal force. So it's measuring that number. The normal force is something that can change. It could get bigger by someone pushing down on you or lighter by someone lifting you up a bit. Your weight, your actual FG value never doesn't change on the earth, but the normal force will. So a lot of these questions basically go where you go in an elevator and they ask about what happens to that normal force when you're in the elevator. Now, if you're moving at a constant speed, then the scale reading has to be the same. That makes sense because if we look at an FBD, constant speed means that the object's in equilibrium. So the normal force pulling up, the force pulling down have to be equal because otherwise it wouldn't be in equilibrium. When the object is accelerating upwards, though, then what you find is that your scale reading goes up and you feel quote unquote heavier. Again, this makes sense because if we look at the FBD, you have the normal force going up and the force of gravity going down. In order for this object to accelerate upwards, the normal force would have to be bigger than the gravitational force. And this is actually one of the reasons why, if you go in an elevator, sometimes if you're starting at the bottom floor and it goes up, you kind of feel that initial moment where like your intestines go down. It's because your body does feel a little bit of heaviness in the very beginning. Usually you don't accelerate for that long and it goes straight into the constant speed. But if you took a scale into the elevator, stood on it, and you saw what happened right when the elevator starts moving, you would see the scale reading actually increase for a brief second. And then the last one is that when it accelerates down, the scale reading goes down and you feel lighter. Again, looking at the FBD, the normal force going up and the gravitational force going down. If it's accelerating downwards, this force has to be bigger. So the normal force has to be smaller than your weight. Um, and again, same idea. That's pretty much it. Now, the one thing I do want to point out is to realize that it doesn't matter the direction you move in. Notice that this entire time I've been saying the direction it accelerates in. You can accelerate in one direction and move in a different direction. That's what projectile motion was all about. You can accelerate up and be moving downwards. So, this entire concept, the scale reading and what its value is, cannot tell you what direction you're moving. It can only tell you what direction you're accelerating in. So keep that in mind. You don't know if you're moving up or moving down. All you know is that you're accelerating up or down. For example, Uh, at the if you're moving upwards in the very beginning of the ride, then your acceleration would be upwards. But if you're moving downwards and you're coming to to a stop, you're also accelerating upwards. So just keep that in mind that there has to be an acceleration in order for the scale rating to change. And this is pretty much the same idea. All right. Again, if you have any questions, please let me know. All this was about the 111 method mainly, and a little bit about the elevator rides. So feel free to send me a message on Remind or come to the extra help. Otherwise, good luck, and I'll see you later. Bye.